Dear students, in the last class we have studied about the new technique which is a sequence components for the study of unsymmetrical fault or unsymmetrical systems. Now, according to the syllabus, we are moving to the next topic which is the representation of power system component like transmission line, generator and transformers in during the sequence component or sequence supplies. So first we will discuss about the sequence impedance of the transmission line. This is the model, the diagram shows this is a model of the transmission line. Here three-phase transmission line is here. Xs is the series impedance of the line and VA, VB, VC is the sending end voltages and VA dash, VB dash and VC dash are the receiving end voltages. This is fully transposed line carrying unbalanced current. The return path for IN is sufficiently away to mutual effect to be the ignored. We have not considered the mutual effect. So only the mutual effect will be in between the transmission line. So mutual impedance is noted by XM from phase A to phase B, phase B to phase C and phase A to phase C. The mutual effect is XM denoted by the XM, but the mutual effect between the ground wire and the transmission line is neglected because we assume that the neutral wire is far away from the line. Now the supply is unbalanced. As we studied, whenever the supply is unbalanced, it means that the supply has three parts: positive, negative and zero sequence supply. So when we apply it, when we supply the unbalanced current IA, IB, IC are unbalanced current, then what will the condition will become here. So we will write the KVL equation here. We can write from the circuit that VA minus VA dash, VA minus VA dash is equals to J into XS into IA plus J into XM into IB plus J into XM into IC. This equation from the KVL equation, that VA minus VA dash, which is the difference of voltages, this should equal to the voltage drop. And what is the voltage drop? That is JXS into IA in the series case, and in the mutual case it will become JXM IB plus JXM IC. Similarly, we can write the other equations for phase B and phase C. For the phase B, VB minus VB dash will become JXM into IA for the mutual, JXS into IB for the series and JXM into IC for the mutual. Similarly, VC minus VC dash, JXM into IA, JXM into IB, this is from the mutual effect, and JXS into IC, it is the series drop. So this is the voltage drop KVL equation voltage which denote the voltage drops. So this equation is very simply written by the KVL method, Kirchhoff current voltage law. Now from these three equations we can arrange in the matrix form. Then we arrange this in matrix form. VA, VB, VC minus VA dash, VB dash, VC dash can write as J XS, XM, 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 XS, XM, 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 XS into IA, IB, IC. Or we can say that if we denoted this matrix is a VP, P for the phase, VP minus VP dash is equals to Z into IP. IP is the phase current, or VP is the phase voltages. So VP minus VP dash it is equals to ZIP. Up to that we have just written as a KVL equation for the given circuit. Now we have studied that in the previous lecture that if we want to convert the phase component into the sequence component, then VP become A into VS. A is the matrix. So we can write here VP is equals to A into VS and VP dash is equals to A into VS dash. So it will become A into Vs minus Vh dash is equals to Z. Ip will become AIS. So we can write here Z into A into IS. Further, Vs minus Vh dash will become, this A is gone in this side, it will become A inverse into Z into A into IS. We cannot simply cancel it from A to A because this is a matrix. So it will become A inverse into Z into A into IS. Now we can calculate the value of A inverse into Z into A. A inverse into Z into A. The value of A inverse is also derived in the last class. It will become 1 by 3. 1 alpha alpha square, 1 alpha square alpha, 1 1 1. Z, the value of Z is taken from the above equation. The value of Z here. And A, the value of A matrix, which is also taken from the previous lecture. So this is A inverse into Z into A. If we multiply all the three matrices, then the value which is come here, it will become J xs minus xm 0 0 0 xs minus xm 0 0 0 xs plus 2xm. So our equation will become, when we put this multiplication value in the equation number in the above equation in this place, then our equation will become Vs minus Vh dash. Vs means sequence component, or we can write it as V1, V2, V0. Positive sequence, negative sequence, or zero sequence minus V1 dash, V2 dash, V0 dash. It will equal to Z xs minus xm 0 0 0 xs minus xm 0 0 0 xs plus 2xm to I1, I2, I0. Or we can write it is Z1, Z2, Z0, I1, I2, I0, and V1 minus V1 dash, V2 minus V2 dash, or V3 V0 minus V0 dash. If we decouple this equation, or again if we want to write this equation, here Z1, the first we define the Z1. Z1 is the, we assume that xs minus xm, jxs minus xm, it is denoted as a positive sequence impedance. Xs minus xm, it is negative sequence impedance, and Z0 xs plus 2xm, it will be zero sequence impedance. Because these three equations does not affect each other, means it is decoupled equation. If we want to write the if we want to open this equation or open this matrices, V1 minus V1 dash will become Z1 into I1. V2 minus V2 dash will become Z2 into I2. V0 minus V0 dash will become Z0 into I0. But there is no effect of I2 in the equation of positive V1 minus V1 dash. Similarly, there is no effect of I1 in the equation of V2 minus V2 dash or V0 minus V0 dash. Means these three equations are the decoupled equation. So we can simply write as V1 minus V1 dash is equals to Z1 into I1. V2 minus V2 dash will become Z2 into I2. V0 minus V0 dash is equals to Z0 into I0. So the value of Z1, Z2, Z0 is name is given as a positive sequence, negative sequence, and zero sequence impedance. To conclusion we can made here that the value of the positive sequence impedance and negative sequence impedance are equal, whose value is xs minus xm, and the value of zero sequence impedance is something different, which is greater than from the positive and negative sequence impedance, which is xs plus 2xm, because some value is added in the xs, while in the positive negative sequence impedance some value is minus from the xs or series impedance. So the conclusion is that if we provide the positive sequence supply, positive sequence means if you whatever we studied here, whatever we studied up to that in the machine or other power system, which is positive sequence means A B C, and with the interface difference of 120 degree, if we provide such type of supply to the transmission line, the impedance which is offered by the transmission line is xs minus xm. Similarly, if we interchange the phase, any two phases A, C, B, then the similar impedance will offer the transmission line, which is xs minus xm. But if we provide the zero sequence supply to the transmission line, means all the phase are co-phasal, then the impedance offered by the transmission line is something different, which is greater than the positive and negative sequence impedances. We can also make the separate, because these are equation are the decoupled equation, we can make separate network for the positive, negative and zero sequence network. This is called the positive sequence network, negative sequence network and zero sequence network, where v1 minus v1 dash will become z1 into i1, v2 minus v2 dash become z2 into i2, v naught minus v naught dash will become z naught into I naught. So this is the derivation, and this is the study of the transmission line. Whenever we provide the unbalanced supply, or whenever we given the sequence supply, positive, negative and zero sequence supply to the transmission line. In the next class we will discuss the our next power system component, which is the synchronous machine. If we provide the synchronous machine an unbalanced supply, then or we can say we provide the positive, negative and zero sequence supply to the synchronous machine, what impedance will machine offer, we will discuss in the next lecture.